So in this chapter, we talk about a bunch of different topics to do with light acting as a wave, and we start with single and double slit refraction. So let's do for the first couple of questions on double slit diffraction. So we said that monochromatic light, which means a single wavelength, a single color, passes through two slits separated by 0.0324 millimeters. If the angle to the third maximum beyond the central peak is 3.51 degrees, what's the wavelength of the laser? So what goes on in double slit diffraction? We have two slits with a distance d in between them. Light comes through it and it forms a pattern on a screen or on a wall where you have a central peak and then you have other smaller peaks beyond it. So what we're told is we want to know the third peak beyond the central peak. So we want this one over here. So remember, these are numbered by m. M equals 0 for the center, m equals 1, m equals 2, and m equals 3. So we want the m equals 3 peak. Okay, so what are we told? We're told that the d spacing is 0.0324 millimeters, and remember, always put everything into SI units. 3.24 times 10 to the minus 5 meters. All right, the angle to the third maximum, so we know that m equals 3, and the angle is 3.51 degrees, so theta is 3.51 degrees. We want to know what's the wavelength, so that's lambda. Okay, so what equations do we have? So we've got d sine theta equals m lambda for our maximum. And, oops, I forgot my theta in there. And d sine theta equals m plus 1/2 lambda if it's a minimum. So since in this case we're talking about a peak, a maximum, constructive interference, we're going to use this equation. So we've got d sine theta is equal to m lambda. We know our d, we know our theta, we know our m, so we just have to divide both sides by m to solve for lambda. So lambda is equal to d sine theta over m, and just plug and chug. So d, 3.24 times 10 to the minus 5. It's important you put it into meters. Sine of 3.51 and divide by 3, and so I get lambda is equal to 6.61 times 10 to the minus 7 meters. And what wavelength is that? Remember, usually when we talk about things in the visible spectrum, we turn into nanometers. So this is equal to 661 nanometers, and that's red light. Okay, so it's not important that you do this last part, okay, but it is important that you get that final answer. Okay, so let's do another one that has to do with the projection on the screen. All right, so let's see what we've got. Light with a wavelength, lambda of 546 nanometers. So again, put everything into meters. 5.46 times 10 to the minus 7 meters. Remember, 1 nanometer is 10 to the minus 9 meters. Passes through two slits, so I know it's a double slit problem, and forms an interference pattern on a screen that's 8.75 meters away. So when we draw our picture, quickly sketch it over on the right hand side. We know the distance to the screen is 8.75 meters, right? And usually we call that distance L. So L is equal to 8.75 meters. And let's see, if the linear distance on the screen from the central fringe to the first bright fringe, so a fringe is the same as a peak. Okay, so what we're saying is that the distance between the center peak and the first peak is 5.16 centimeters. And we usually call that y. So y is equal to 5.16 centimeters. And again, I'm going to put it all in meters, 0.0516 meters. And we need our m value. So m equals 0 for the center peak, m equals 1 for the first peak. All right, so that's everything that we can get out of there. So let's see, we want to know what is the slit separation is what we're trying to find. So D equals question mark. All right, so what are our equations that we have? Well, we have d sine theta equals m lambda. So we know lambda, we know m, we don't know d, we don't know theta. So we can't use that equation right now. Is there another equation that we have? Yeah, we have the equation for, let me do another color, go to blue. So if we have our rays of light coming in through the slits, we talk about, we're trying to find that angle in there for the triangle. So if I look at this, y is opposite and L is adjacent. So let me just draw my quick lip triangle over here. So I've got y and L and theta. So what I know is that tan of theta is equal to y over L, and I do know y and L, so I can use that to give me my theta, and then once I have my theta, I can plug it back into the equation that I have there in red. Okay, so y is 0.0516 meters, L is 8.75 meters, so I get tan theta is 0.005897, so theta is equal to the inverse tan of 0.005897, which is 0.338 degrees. Sometimes you see problems in books where they just take y over L and they substitute that tan theta value in instead of sine theta. And that's approximately correct when you have a number that's as small as this. But if the number isn't as small, your final answer for the angle is going to be a little bit off. So it's always more correct to do it the longer way, like I just did, to actually get the angle and then plug the angle in. All right, so let's go back. So now I'm going to use d sine theta equals m lambda. So d is equal to m lambda over sine theta. So m is 1, the wavelength, 5.46 times 10 to the minus 7 meters. And now we have the sine of 0.338, and I get 9.255 times 10 to the minus 5 meters. Okay, so that's about 1 micrometer. It's a very, very small, about 1/100th of the diameter of one of your hairs. So it's a very, very small separation between the two slits that causes light to diffract. And so if I were to, like the first problem, they had the slit separation in millimeters. If I were to do that, that'd be 0.093 millimeters. So if you can do problems like first problem and the second problem, you might also have one where you're asked to do it for a minimum rather than a maximum. You should be good at doing any problem that you see on the test for double slit diffraction.